Okay, off we go. So, good to see y'all again. I think it's been a week since I've seen you. I guess we had a holiday on Monday and snow day on Wednesday. So anyway, here we are again. Okay, so last time, we were well beyond what I have on the screen right here, but, so I had a conversation with some other of the instructors of this course, and we were talking about this part right here where you're gonna need to make your choice of convention unambiguously clear. You know, that is, if there is no established convention already, right? But in a situation where you get to decide, again, and you do have to make your choice clear, we agreed that the following would be a very efficient and reasonable way to make your convention clear. And that is to, in parentheses, indicate, separated by commas, the three, variable names that you're going to use to represent the spherical coordinates specifically in this order as I have indicated here. Right? So first, now just to make it geometrically, so first the what we'll call the radial distance. That's what Kali calls rho. Second, what we're going to call the vertical angle. Right? So what Kali calls phi. And then third, the what I call the horizontal angle, which Kali calls theta. So it's specifically in that order as listed here, and then in parentheses. So just as a for example, a real convenient way to do this, if you choose to do spherical coordinates and you want to do it using Kali's conventions. For what to call the spherical coordinates, then this right here, all you got to do is just write like so, and your convention is established. Now, again, it remains, you do have to be consistent. So once you set what notational convention you're going to use, you have to stick with that, right? You can't sort of switch in and out, right? That would be then we wouldn't be able to interpret what you're saying reliably, right? So that's off the table. You do have to be consistent once you make a choice, and that's the easiest way to establish your choice. Okay, alright, so I just wanted to hit that real quick. We are gonna move on now to section 2.3, picking up where we left off. I'll say last time, that being, of course, the snow day where you watched the recordings where I did this stuff. Okay, so finally, some multivariable calculus, right? What is it, 3 weeks into the course, and we're finally doing a little calculus. So we're going to talk about derivatives, and the very first thing you need to know about multivariable derivatives is there's not just the one, like in single variable. In single variable, there's just a derivative, right, as far as first derivatives go. I mean, obviously there's second derivatives. But there's just one kind of derivative. So not so in multivariable. There's several different kinds of derivatives. We're going to see 3 of them today, if I remember correctly. So several different kinds. Why do we use the same word to describe things that are different? As you will recall, that's one of my little pet peeves, right? I feel like if you have different things, if it is important that they're different, they should have different names. Fair. The reason we use the word derivative, at least in connection with all of these things, is that they have something in common. They all relate input changes to output changes. This is going to be my cornerstone point of view on what is a derivative in this course. It's something that relates input changes to output changes. In different ways in all of these cases, of course, right? But nevertheless, they all have this unifying feature. They relate input changes to the function to the resulting output changes from the function. Okay, so we're going to start with partial derivatives. Now, again, just a little context, I'm not super happy about that. Now, I am going to start with partial derivatives for, a combination of reasons. They are easy to compute. That's awesome. We're going to love that. It's really nice how they work out. They are very relatable. That makes it an easy first step to take in talking about multivariable differentiation. Yeah, great. Nice little first step starter move. The book does it this way. That actually swings some weight for me. Obviously, I don't do everything exactly the way the book does, but the bigger deviations I take, the more cost there is in sort of confusion with the students. And so there's always a trade-off to be met there. And frankly, I think sticking with the book on something like this outweighs the cons. So be it. But let the record show. That doesn't mean I think this is the right way to do it. There are some pretty significant disadvantages to starting with partial derivatives. And this is what I think is really the biggest one. I feel like we should start with the thing that's the most important. Not the thing that's the easiest. The thing that's the most important. And I don't think partial derivatives are it. Now don't get me wrong. Partial derivatives are important. They're computationally essential. Yeah, sure. Right, absolutely. But in terms of understanding multivariable derivatives and how you should think about them and the intuition that you know, 50 years from now when you're thinking back on multivariable calculus, I hope partial derivatives are not what you remember. I hope that what you remember is that derivatives are a way to relate input changes and output changes, and the best way to do that is not partial derivatives. This is a little foreshadowing. So anyway, something to keep in mind. And with this disclaimer set, here we go. Let's define partial derivatives. It's a two-step process. Step one, basically take your multivariable function and we're going to turn it into a single variable function by taking most of the input variables and just deciding, you know what, we're going to treat those like constants. All except for one. You're going to pick one variable not to treat as a constant. That's going to be your remaining variable. That's the variable for the resulting single variable function. Now, before we go on to step two, reasonable question, reasonable concern you might have is, wait a minute, can I just play make-believe? Is that okay? Can I just make stuff up? Can I take things that are obviously not constants and just, I'm going to decide that they're constants now? And, well, I mean, there's a cost to be paid there, sure. When you make stuff up, what you conclude as a result only makes sense on that assumption, right? So we're not defying the truth here. We're just saying if we were to treat them as constants, then what would be the consequence, right? So, yes, you are allowed to make stuff up. Cost, what you conclude, is correspondingly narrow, right? So, okay. So we're going to treat all these variables as constant except for one that produces a single variable function. And then step two is take the usual derivative, just regular old, plain old derivative. Calc 1 style. Okay. All right, now we're going to do some examples on the next page, but first a little quick thing about notations. This is the more standard notation, I think, for writing a partial derivative. The thing to be aware of on this is that symbol right there is not a D. It's very important that it's not a D. If you put a D there, it means something different. You cannot choose to use a D instead of that new symbol. You have to use this new symbol. And I know it's a little annoying, but this is something that matters, and so you do have to be careful with that. So please, heads up, right? And by the way, for whatever it's worth, there have been several times in my mathematical career where I've taken a class that introduced a new symbol that I have never used before, and I had to go through the kind of humiliating process of having to take myself back to basically, what is that, second grade, where you're first grade, second grade, where you're practicing how to make your letters, right? And I had to do it all over again. And so I filled up pages kind of practicing, kind of rehearsing, how am I going to make my partial symbols? And I did it for various Greek letters, and I did it for various other kinds of letters, and it's silly and humiliating, but you kind of have to do it. You got to make sure that you can actually, as required, make that new symbol. Okay, that said, let's see here. Let me get back into this mode. It is not the lowercase Greek letter delta. You can't do that either. Again, unacceptable. It's not what that means. It's something different. You do have to make the correct symbol. Okay, alrighty. So that said, let's do one. Let's actually compute a partial derivative. This looks like a hard one that we're starting off with. Look at this monster. It's a product of three factors. One of them has a composition, and it has something ugly inside of the composition. This looks like a nightmare of inconvenience. This is actually a super easy one, believe it or not. And it's because of, in this process, keep in mind the first step is to hold all the variables constant except for one of them. Whichever one you're taking the partial derivative with respect to. That's the only one that you don't treat as a constant. So, sure, y is a variable. That means y squared is going to be something I'm going to have to take a derivative of and treat as not being a constant because it's not a constant. But x is a constant. That means e to the x is constant. X is a constant, z is a constant, that means this thing here is a constant, that means this whole thing here is a constant. Great, big, ugly, sure, but still constant. So what we have here is we're taking we are recognizing this as being a single variable function of y, and that function is constant times y squared. And it doesn't matter how ugly the constant is. Is everybody on board? How are we doing? Everybody see I'm just following the rules, right? Okay. So the actual action of taking the derivative with respect to y of y squared, of course, very easy to do. 2y, everything else is a constant. Rewrite it in a way that looks a little prettier on the page, and you're done. Okay. All right, so I nominate partial derivatives as being the easiest derivatives to compute. They are easier, I would propose, easier than single variable derivatives. Because when you're looking at a single variable derivative, you don't get to just, ignore basically huge fractions of your expression. Right? So, totally awesome. Okay. All right, couple other examples. I'm going to let you do most of the reading on the details of this because y'all are experts at single variable derivatives. This one looks like a scary one because we have a function to the power of a function. Do y'all remember logarithmic differentiation from Calc 1? It's a neat trick for how to take, when you have a function to the power of a function, the standard rules don't really address how to deal with that. It's not a power rule, it's not an exponential, it's kind of a combination of both in some weird way. Logarithmic differentiation is a trick for dealing with that. And that's what this looks like, but it isn't. Because here we are taking a partial with respect to x. So that's a function, sure, but y is a constant. That means that whole exponent is a constant. This is nothing more than a power rule question. And don't forget the chain rule, of course. So, very often, they're easier than they look. Y'all can read the next one. It's pretty straight read. So, we're going to talk now a reasonable question. Let me go back to the definition here. I did some pretty serious making stuff up here. Right? So, having made up arbitrarily something that seems completely unfair, when I do this process, when I compute this thing called the partial derivative, is it useful in any way, or did I just make up enough nonsense that this is meaningless garbage? Right? And that's something you should be concerned about whenever somebody says, hey, I'm going to play make-believe in the following sense. You should think, okay, well, convince me that that's not nonsense. Right, so I owe you an explanation that this is not nonsense. Okay, so here we go. What we're going to do to address that concern is we're going to think about the geometric interpretations of partial derivatives. Now, that is, if we're going to take partial derivatives of a function, what does that look like in the picture? And the very first thing, of course, and you all heard me harp on this quite a bit over the last few lectures, is, well, it depends on what kind of picture you're looking at, right? The graph construction that creates this picture that we call a graph. The graph construction, totally different from the level set construction, right? Which is totally different from, well, if you look at a function and ask, well, what does that parameterize, right? The what we call the image of a function. Totally different relationship between algebra and geometry. So if you want to know how to interpret an algebraic operation geometrically, you've got to decide which picture you're looking at. And again, I know I say that a lot, but that's because it's important. So we are going to ask this question, geometric interpretation, first. We'll get to the others later, but first in the context of graphs, right? So we're going to take our function and we are going to look at the graph of that function. Keep in mind, graph means you're going to set the output values of the function equal to a new variable. In this case, I'm going to use z. Okay, so in the graph context, there's our graph. If I am at a point in the domain, a comma b, and if I want to take the partial derivative with respect to y, what does that look like on this picture? Everybody see the question and setup? All right. Okay, so, well, here's the good news. This process of taking a partial derivative is a two-step process, and both of those steps have an existing geometric interpretation that we already know, and we just have to kind of fit the pieces together. So this is just a follow your nose argument. Let's see here. The first step in taking the partial derivative is to fix the other variables. Y is the one we're taking the partial with respect to, so x is the other variable. Now do keep in mind, we're starting off at a point where x is a. So when we say fix x, and it's already got the value a, then I have to fix it at that value a. And that equation, x equals a, is a plane that looks like this. In particular, that's a vertical plane, right? In graph world, right? In the three-dimensional world that we create when we talk about graphs, that is, as it turns out, a vertical plane. And furthermore, it's a vertical plane perpendicular to the x-axis. And being perpendicular to the x-axis, I'm going to point out that means that plane is kind of going, if you will, in the y direction. How we doing? Everybody see that? It's easy to get this backwards, by the way, and get confused. Okay, wait a minute. So I'm setting which one constant, and so the plane is perpendicular to which and parallel to which, and it's easy to get that messed up. Be careful. Think it through. Make sure you get that straight. Okay, now what's the consequence? What's the geometric consequence of making this choice of setting x equal to a? Well, I had started off, I was looking at a graph of a function of two variables. That graph was a surface, but when I set x equal to a, that means I'm looking at what's happening in that plane. That means I'm in fact looking at this cross-section, which of course is just a curve. Alright, so step one, this process of fixing the other variables, what that does is that gives me a curve. Now, what kind of curve does it give me? Well, here's the beautiful thing. We started off looking at a graph, right, where height, z, was telling me the value of the function. Now, looking at this curve, it remains that the height, the z, is still telling me the values of the function. It's just telling me the values of the function as y changes along the line specified by that value of x. So said differently, what we are looking at here, this orange curve, is in effect the graph of that single variable function that we made by fixing x. And good news there, because we already know a lot about graphs of single variable functions. In particular, if you're looking at the graph of a single variable function, and you take the derivative gives you the slope of that tangent line. Again, something we already knew, right? That's a Calc 1 thing. Okay, so that's nice punchline. Really convenient little punchline. If you are looking at the partial with respect to y, the geometric interpretation in the graph context, cannot emphasize that enough. The following only makes sense if you're looking at a graph of the function whose partial you're taking. Partial with respect to y is the slope. To be clear, it's the slope of the tangent line. To be a little bit more clear, it's the slope of the tangent line in the direction of the axis of the variable that you're taking the partial with respect to. So y partial is the slope in the y direction. Is that cool? Is everybody happy with that? All right, so I'm going to leave as an exercise. I think this is a really healthy exercise. Think through the equivalent argument for what if you're taking the x partial. Now, you could probably guess, noticing a pattern, perhaps, you'd probably guess that the x partial is going to be the slope of the graph in the x direction. And that's true, it is, right? But it's important that you not just take that as the result of a pattern, right? Not all patterns hold. So think through the argument, right? And specifically, I think it'd be a healthy exercise to draw these corresponding pictures, right? Think it all through. Think through the little detail devils, and come to this as a conclusion of an argument. So excellent little practice exercise. As always, come to office hours if you want help on this. If you get stuck, you're not sure how to get started, whatever, I'll be happy to help you through it. Okay. All right, moving along. Okay, so that was graphs. Now, we're still interested in partial derivatives, but now we're going to entertain a different question. What do partial derivatives look like if we're not looking at a graph? What if we're looking at this literal picture? Right? Now, what does a derivative mean? It's not a graph. It's not a slope, because this picture is not a picture of a graph. Now, again, you're going to have a line in your head, right? Sort of a barrier, and calculus of graphs. When I take derivatives, what does that look like geometrically on a graph? And then a bright line, and then a totally different set of ideas over here, which is going to be the calculus of the literal picture. And they're completely different, because it's a completely different way of looking at pictures to understand functions, completely different, construction, you might say. So we're going to get a different answer. And here we go. Let's talk about the partial with respect to y again. Well, that means that x and z are constant. That means x and z have to stay at these values, a and c. That means that I'm going to be moving in the y direction, right? And if I move in the y direction by some amount, that means that my position differential, how far does my position change? What vector represents my change in the domain? Well, there it is. It's that what I'm calling dy. And it's entirely in the y direction. Of course, if you do that, there will be a resulting change in the value of the function, df, which of course we draw over there. And I'm sure you all remember, we have an existing interpretation of derivatives, right? They're the relationship between input changes and output changes. In this case, the partial derivative is what you multiply by the input change to get our output change, or at least our linear estimate of the output change. So now again, I like to emphasize, where's slope in this picture, right? It's not in the picture. When you're looking at the literal picture, this is not a graph, and the graph interpretation doesn't make any sense here. So not a slope. Right? Again, bright line. You got to keep your calculus. What does calculus look like in the graph context? Completely separate from what does calculus look like in other contexts. And here's what it looks like here. Alrighty. Moving along. What about level sets? Reasonable question. Right? Another kind of picture. Another bright line. We're going to have a totally independent and separate calculus of level sets. Right? And here we go. So let's see here. Let me zoom in a little bit here so we can see better, so I can draw more easily. Let's think about what would happen if I want to take the partial with respect to x. Partial with respect to x. Now the first thing I have to do is hold y constant. Right? If I'm going to hold y constant, that means that I'm stuck on that line where y is a constant, which of course means that I'm going in the x direction. And okay, that being the case, let's try to understand this partial derivative here with respect to x. By the way, just to make the picture a little easier, let me draw some of these, let me emphasize some of these level curves. So, for example, that might be where f is equal to, let's say, 300. Maybe this, I like to think about topographical maps when we're looking at level sets, because there's something, viscerally relatable about that. You don't have to, but I like it. So if that's the 300 altitude contour line, then this is the 400, perhaps, and then this is the 500. Right, and now let's consider what happens as I move in the x direction. And oh my gosh, look at this! I've got to gain 200 feet of altitude over a very short horizontal distance. And I got to tell you, that looks like it's going to be a tough hike. Right, that looks very steep. In particular, if I were to imagine what the graph would look like here, height as a function of or height being the value of the function. That in fact would basically reproduce the mountain itself, where in fact height is the function, right, that you're looking at. Right? Height is altitude. So I think that'd be a steep mountain. I think that means that the graph would be steep, and that means that the value of the x partial is large. How large? I'd need more information. I'd need to have some sense of scale of the horizontal distances, and I'd need to have more information of, are these values of f, are those in feet? Are they in meters? What are we doing? Right? So you can't actually determine the actual value, but you can tell that x partial is going to be, it seems like it's relatively large. Okay. That noted. Let me see here. Now let's entertain, what if we are, oh gosh, can I delete? Yeah, there we go. What if we were going to look at the partial with respect to y? Right, what's the partial with respect to y? Well, I would notice if I go in the y direction, I'm gaining those same 200 feet of altitude, but over a much greater horizontal distance. Oh, that's my kind of hike at this point, right? I don't want to go straight up the cliff. I want to walk around, right? I want the longer, more circuitous, more leisurely way of getting up to that higher altitude, spread it out over a greater distance. That means it's not as steep. That means the graph is not as steep. That means that the partial derivative is smaller. What do you think? Everybody buy it? So the punchline then, how do we without having to think about graphs all the time, right? If I want to just look at this picture and instantly make some inference about whether the partials are large or small in comparison to each other, basically the idea is you want to see how close together are the lines. And let me zoom in more. Oh, if I can. Gotta get this out of the way. There we go. Okay. So zooming way in here. Oh. Okay, there we go. Notice in the x direction, the lines are relatively close together. In the y direction, they're relatively far apart. And that's basically how you tell. Right? Close together means a large partial derivative. Farther apart means a smaller partial derivative. Okay. All right. Okay. Let's see here. Moving along. Okay, so let's talk about linear approximations. This is a nice foot in the door to some excellent conclusions that we're going to need to get to, and this is a nice way to go about doing it. So I'm sure y'all remember linear approximations from your Calc 1 classes. This formula in particular, I'm sure you've seen. So let me say, make sure you're good at all of this single variable linear approximation stuff. Now, there's different ways to think about linear approximations. There is a particular, specific take on partial derivatives that I think is really helpful on linear approximations that I think is really helpful, and that specifically I want to take that point of view on linear approximations here. The linear approximation is the unique degree 1 polynomial that has the same value as the function we're interested in at the given point A, and that also has the same first derivative as the function that we're interested in at the point A. So, said differently, the linear approximation is the mimic. It's copycatting. It's trying to impersonate f in value and derivative at the point A. And there's exactly one degree 1 polynomial that'll do that. In many cases, I should say. So that is a little asterisk that I have to come back and recognize here. Sometimes there is no linear approximation, right? Exactly what are these scenarios, and exactly how do we know when this problem of, there isn't really a good way to linear approximate a function, how do I see that coming? We'll talk about that in a bit. Right? But so for the moment, we're going to assume that the linear approximation exists, and if that's true, there will be exactly one such thing. Okay, now I want to make sure that y'all can prove that these two properties hold. So I'm going to leave that as an exercise. It is pretty plug and chug. Let me point out what it is that's very commonly the stumbling block that a lot of students mess up. A lot of students mistreat this part right here. That looks like a formula. It looks like a function. And it kind of isn't. In fact, that's a constant. F prime of A is a constant. F prime is a function. F prime is a function of X. Yeah, sure, but that's not what this says. This says take that function F prime, now plug in this constant value A, this number that doesn't change, just plug that in, and then what you're going to get out of that function as F prime of A is just some value. Right? It's a constant. So when you're looking at item number 2 down here, when you're trying to figure out, how do I compute L prime so that I can plug and compute and confirm that this works, as you're computing L prime, don't forget that that is a constant. Okay, all right. The rest y'all can make sense out of it yourselves. And again, as always, come to office hours if you have any questions. But make sure that you can prove both of these results from this formula. Okay. All right. Okay, so that said, We're going to try to do something similar now in the multivariable context. Very similar. Multivariable, you see we have n input variables. Goes a multivariable function. And I want to find the unique first order polynomial that agrees with f in value. And now let me be careful about this second statement. I want it to agree in derivative, but wait a minute, what's a derivative? We've got a multivariable function. What's a derivative anyway? Oh gosh, well the only derivative we have so far is partial derivatives, but there's several of them. Right? You can talk about partial derivatives with respect to any one of the input variables. There are n input variables here. So there are n different partial derivatives. And when I say I want L to agree with f in first derivative, I mean all of the first derivatives. L has to impersonate f for all of those first derivatives. Okay. And there is a formula for how to do this. Here it is. I claim it has a lot in common with this formula from single variable. You'll notice it starts by just plugging in, f of a, right? So you start off with whatever that value is. And then you have a bunch of terms, each of which individually kind of looks like that term. And notice again, what we have is a constant times a difference. Now this is the difference between the base point and the variable where you're evaluating. This is likewise, but just the nth coordinate of the point where you're evaluating minus the point where your where your base point is. Okay. So again, a common mistake that students make when they're trying to make sense out of this formula, when they're trying to prove this property number 2 down here, is as students compute the partial derivative of this L function, very often students forget to treat this as a constant, because it is a constant. It's being evaluated at a, and let me address a notational point here. This, vertical line after an expression with a little subscript indicating a point, that's just an alternative notation that says, hey, evaluate that at that point. It's just an alternative notation. Why did I use this alternative notation here? Well, I don't know. It makes me feel a little uncomfortable when there's 2 parentheses next to each other that aren't actually multiplications. I feel like if I were to put a in parentheses there, and then I have xn minus an in parentheses, it looks like you're supposed to multiply them, which of course you're not. That's just not what that means. And I don't like ambiguous notation if it can be avoided. So this is an easy way to avoid that ambiguity. So heads up, you'll see that in various places. Okay, so don't forget to treat that as a constant. And again, make sure you can do this. Make sure you can indeed confirm that this expression that we just wrote down there has these desired properties. Okay. Alrighty, moving along. You're going to notice that in this expression, these terms do something really nice. Those terms there are a sum of products of factors, just like a dot product is. Right? I mean, structurally, this is a sum of products of pairs of factors. It is a dot product. So, that's awesome. Right? Dot products are great. We know properties of dot products. We know how to interpret geometrically with dot products. So, the fact that our formula here has something in common with dot products, we do not want to let that just slide on by us. That's going to be useful. So this being a dot product, we need to figure out what are the two vectors that this is a dot product of. Now the first part of that is actually pretty easy. If you look at those factors, those are literally the coordinates of the vector x minus a. So that one, the fish just jump in the boat sometimes. That's an easy one. That's the vector x minus a. Now we've got to figure out, okay, what about those orange things? What is this vector whose coordinates are the various partial derivatives of our function f? I mean, there it is. That's what the coordinates are. I need to know what is this vector that has those as coordinates. And, well, we have not previously seen such a thing, so we're just going to define that to be this thing that we call the gradient. And that's just so, right? For the moment, we are defining that to be this thing called the gradient, just so that I can rewrite this big blue expression as a dot product, which of course it is, but that's our goal. So we defined the gradient with this in mind. I'm going to just get rid of all of that. This is called the gradient of a function. For the moment, all you need to know about the gradient for now is that it's a notational convenience. It's this vector that is defined by the partial derivatives, the coordinates of the partial derivatives, and it makes it easier to write this expression more compactly. Notational convenience only. For now. We're going to find out that it's actually much cooler than that. Okay. All right, so let's do one. How would I form the linear approximation of this function at that point? Well, we're going to follow the formula here. Let's see here. I'll do it like this. We're just going to plug and chug directly into there. And this is very plug and chug. Now, I'm sure y'all can plug in a into the function and confirm that the value of the function there is 5. That's very doable. That's just arithmetic. Now, the next thing I need to do, though, you'll notice I do need to find the gradient. Namely, I am going to need to talk about all of the partial derivatives of, well, let's see here. I need the gradient of f. So all the partial derivatives of f, I'm going to have to compute. Now, we just talked about partial derivatives. We just made that definition. So make sure you can do that, right? You got to compute those partial derivatives. Don't forget when you're computing partial derivatives, you've got to be careful in your mind. What's a constant and what's a variable? And treat them as such. Notice since we're taking a couple of different partial derivatives, for one of these, x is a variable. For the other, x is a constant. And vice versa. Right, so you got to be careful with that. And then, of course, we're going to plug in the point A. There's A. And plugging in the point A gives me my actual gradient at A, which ends up being then that. Yeah?
How do the constants go away for these constant derivatives?
Say one more time.
Why isn't the first one 2x plus y squared?
Because when you're taking a partial with respect to x, y is a constant. And when you take a derivative of a constant, you get 0. So yeah, that's exactly, you see how easy it is to make that mistake, right? It sneaks up on you because you're accustomed to thinking of y as a variable. And that's exactly what you have to watch out for, absolutely. Yeah. Alrighty. So there we go. We have the gradient there, and golly, it looks like we have the gradient. That means this is the linear approximation, and I think I may be out of time already. Let's see, I have 30 seconds. Okay, I'm sure I owe y'all 30 seconds. So we're going to draw the line right here. We'll pick up there on Monday. Y'all have a good weekend. See you later.